Here's a presentation for the shortest path project. My name is Mei Yao. I'm from section 8B. For context, we're building a scene finder interface for the picture object. The goal is to find the least noticeable seam, aka the shortest path, from this side to the other side of the picture. We define X to be the column, Y to be the row. The adjacency list and generative are two implementations that uses weighted graph to represent the picture object. In the pixel graph, we have three kinds of node: the source node, the sink node, and the pixels. Our first deliverable is to adapt the code from the given adjacency list to implement generative. We'll begin by looking at the source node, which is this one. The similarity between these two is that they both connect the source node to the first column of the pixel. So we will borrow the for loop from y equals to 0 to y equals to picture.height. They also create edges from the source to the target pixel with the weight computed by the energy function. The adjacency list computes all nodes in the constructor and store them in this 2D array called pixels. So they can just use the double bracket with 0, j coordinate to access two nodes. But for generative, it doesn't have any storage. It creates new pixels on demand. So we'll put 0 y coordinate to the pixel constructor. Every time we call source.neighbor, we need to recompute these nodes. For the sink node, there's no differences between their neighbors function. They both return an empty list because the sink node doesn't have any neighbors. For the constructor, I'm adapting the idea of how adjacency list connects a given pixel to its right up, right middle, and right down neighbors. Specifically, this line of code where it iterates across y minus 1, y, and y plus 1, using x plus 1 to access the right column. The similarity between adjacency list and generative is that they both use graph representation of the picture. That allows us to access or generate pixels using xy coordinates. The difference is that adjacency lists create every single node and store it in the pixel graph ahead of time, but generative only creates vertices and edges on demand. So only when pixel.neighbor is called. We're essentially taking a lot of these work and repurpose it in the pixel.neighbors. So you can see the for loop over here. We create a new pixel instead of accessing it from the 2D grid. Another key difference is that in the constructor, we're doing a for loop to connect all the rightmost pixels to the sink node. But for neighbors, we only check if it's at the rightmost. Sorry, it's a typo. We'll immediately return the sink node if it is. EP Sim Finder is the last implementation that uses a table instead of a graph to represent the picture. We choose the lowest energy predecessor by comparing the energy of the given pixel's left up, left middle, and left down neighbors. So similar pattern from before, except we are accessing the x minus 1 column. Once we find the lowest energy predecessor, we compute the total energy cost by adding it to the current pixel energy, and we store it to the DP table. We handle boundary pixels using this if condition. So if c is smaller than 0 or greater than the picture height, it wouldn't enter the if condition and try to access index out of bound. Once we compute the DP table, we backtrack from right to left, because remember, all the pixels in the rightmost column stores the total cost that is accumulated by the minimum predecessor to the left. We find this pixel using two local variables. One keep track of the y coordinate, the other keep track of the minimum energy so far. As we traverse from 0 to the length, we consistently compare and update these variables. We continue to follow the path back left by choosing the prior neighbor with minimum energy cost. I use two more local variables. So the min y is the right pointer, the pred min y is the left pointer. So you can imagine if min y is column 6, then pred min y will be column 5. Using min y, or the right pointer, as the anchor, I will compare its left up, left middle, and left bottom neighbors. Once we find the minimum predecessor, I will update the right pointer to point at the left, add the min y to the result. Ultimately, the find horizontal method will return the least noticeable seam represented as an array list of all the y coordinates. Because we do the collection.reverse, it should be left to right. The fastest implementation in experimental runtime is dynamic programming. The reason being, many pixels can be reached through multiple paths, so recursive solutions like adjacency and generative will recalculate the same subproblems. For DP, each pixel energy is calculated exactly once and stored in the table. This eliminates the redundancy. For the last deliverable, we're comparing the internal mechanism between different implementations of seam finders and shortest path solvers to understand their respective runtime because they kind of blend into each other. Again, adjacency computes all pixels and neighbors ahead of time in the constructor and store them in the grid. So when pixel.neighbor is called, it will return instantly. Generative computes neighbors only when pixel.neighbors is called, and it needs to recompute if it's called again. So there's a lot of repetitions. For the shortest path solvers, topological sorts will traverse the graph 2 times, one for the depth first post order, the other for the edge relaxation. For Dijkstra, it only traverses the graph for 1 time, and it will stop early if the shortest path has already been found. So experimentally, less than all the vertices will actually be considered. Based on these properties, we can tell the adjacency tuple sort would be faster than generative tuple sort. Because tuple sort already traverse the entire graphs anyways, adjacency will be able to store them, have quick lookup if there's any overlapping neighbors that are already computed by previous calls, whereas generative will need to recompute the neighbors over and over again. But generative Dijkstra will be faster than adjacency Dijkstra. Dijkstra only traverses once, and it terminates early if it finds a shortest path early. Adjacency pre-computes all the neighbors, even though they might be useless. Generative would only compute neighbors when Dijkstra needs them. Finally, comparing the tuple sort and Dijkstra, we can see Dijkstra is consistently faster since it's a greedy algorithm. It doesn't have to traverse the entire thing, but it might miss negative edges due to high cost accumulated or there's any early terminations. Tuple sort is safer, but it's consistently slower. DFS will ensure all vertices are visited. So it depends on the use case.